Good afternoon. Welcome to NASA headquarters. My name is Dwayne Brown with the Office of Communications. And today you will hear an amazing story about amazing spacecraft told by amazing people. Today's story, the Voyager spacecraft, humanity's farthest journey. After 33 years in space, they are still operating and returning data billions of miles away from our sun. They also carry a collection of images and sounds from Earth as a message to possible life elsewhere in the galaxy. We have a lot to cover today, so sit back and be prepared for a wonderful story. And the first chapter will be given by Ed Stone, Voyager project scientist and professor of physics, California Institute of Technology. Suzanne Dodd, Voyager project manager, the Jet Propulsion Laboratory in Pasadena, California. Merav Ofer, Voyager guest investigator and assistant professor of astronomy, Boston University. And Drian, creative director, Voyager Interstellar Message Project, and the late Carl Sagan's co-author and widow. So to get us started on that first chapter, I turn it over to Ed Stone.
Well, it's been, as a scientist, it's really been an incredible experience to have been the chief scientist of the Voyager mission since it began in 1972. And it's especially remarkable that nearly 40 years later, the voyage of discovery continues. Today, Voyager 1 is 11 billion miles from the Sun, and Voyager 2 is 9 billion miles from the Sun. But as the first graphic shows, even so, they are still within the bubble that the Sun creates around itself. The blue area is that bubble. It's called the heliosphere. The wind from the Sun blows outward at 1 million miles per hour and creates this bubble. And as you can see in the animation, that the two Voyager spacecraft are in the outermost layer of that bubble, heading toward interstellar space, which is the bright region outside. The mission started many years ago. In fact, the spacecraft were launched in 1977. That was a very special year when the planets, outer planets, were lined up so a single spacecraft could fly by all four: Jupiter, Saturn, Uranus, and Neptune. That's called the Grand Tour. But we didn't start out with that as the ultimate goal. We started out with a more a near-term goal of just getting to Saturn, a 4-year mission to Saturn. Both spacecraft, as you can see in the graphic, flew by Jupiter, got a boost on the way to Saturn. Voyager 1 went behind the rings and therefore went up out of the plane of the planets. No more planetary encounters, but when it succeeded in its mission, that allowed us to keep Voyager 2 in the plane of the planets to continue on to Uranus, which is 19 times as far from the Sun as Earth, and then finally on to Neptune, where it over the pole and downward. So we have a spacecraft heading out to interstellar space heading south, that's Voyager 2, and one heading north toward interstellar space. In the next short sequence, we'll show you some of the things which we saw on this journey past the giant outer planets. First, there was Jupiter, the largest of the giant planets, the mystery of the Great Red Spot. What we discovered was it's a huge hurricane-like storm system 3 Earths across, but it's just one of many such storm systems. Saturn, we flew by Saturn's rings and discovered it's made up of countless particles of icy stuff, BBs, marbles, snowballs, some things as large as houses. On to Uranus, which is tipped on its side with its pole facing the Sun, so it's like a target in the sky when we flew by in 1986. One of the major discoveries was the magnetic pole of Uranus is nearer its equator than its rotational axis. And of course, Earth, Jupiter, and Saturn, the magnetic pole is up where the rotation axis is. On to Neptune, the most remote giant planet, 30 times as far from the Sun as the Earth. So cold we expect it to be very, very quiescent. But in fact, it has the fastest winds in the solar system, even though it has the least energy to drive the winds, and it had a great dark spot. So this journey was really just full of surprises as we learned things we didn't know were there to be learned. And there are two bookends which sort of illustrate that. The first bookend is Io, a moon of Jupiter. Until that time, the only active volcanoes known in the solar system were right here on Earth. But when we flew by Io, we discovered that there were 8 active volcanoes, some of them, as you can see, erupting hundreds of miles above the surface of this tiny little world. And the other bookend was the last body we visited, which is Triton. It's a Pluto-sized moon of Neptune, so cold, 390 degrees Fahrenheit below zero, that even the nitrogen forms the icy polar cap that you see. But those dark streaks of that icy polar cap are the deposits of geysers erupting at 390 degrees below zero on this icy world. Just an example of how remarkably diverse the bodies are in the solar system, familiar in form, but diverse in detail, and has really changed our whole view of the solar system in the textbooks which have been written since that time. But that was not the end of our journey of exploration. There was still the heliosphere. I can't show you a picture of the heliosphere, but I can show you a video of our kitchen sink. So if we could have the next video, because you can see the heliosphere in it. Where the water hits the bottom of the sink, you notice the water is flowing radially outward very fast, just like the solar wind. But eventually, it slows down, but it slows down abruptly in a shock and piles up and forms a thick ring of water. And it's in the thick ring that the water flows down the drain. That's exactly what's happening in our heliosphere. And if we could have the final graphic on this, you'll see that the 2 Voyager spacecraft are in the thick ring. They're in that region just on the whoops, that's not the video, but just on the outer edge of the bubble there, where they're about to break free of the solar system. This now is a computer graphic of this same story, where you can see the wind from the sun radially outward and then turning to flow down the tail. The tail is the drain. All of the solar wind has to go down the drain, which is the tail. Outside, in interstellar space, there's another wind which is coming and flowing around. This wind is slower, but it's still a very fast wind, flowing around outside the heliosphere itself. So there's a separation between the inside and the outside. So what else is outside? What's outside is really the result of a cloud, which in the next graphic we can see the cloud, which is an artist's sketch of what we believe is outside by Frisch and Huff, based on data they've taken from Earth-based telescopes. And there's the sun. It's moving around the galaxy. And also there's this cloud, which has just enveloped the heliosphere about 100,000 years ago. That cloud was formed by the explosion of a number of nearby massive stars 5 to 10 million years ago. They ejected most of their atmosphere and created these clouds, and that cloud is essentially moving and enveloping our solar system. So we are trying to get outside of our bubble into interstellar space to directly measure what is there. The next final slide I want to show is an example of what one of these things look like. This is actually a WISE image of an astrosphere. Around that star, there's an invisible bubble you cannot see, but you can see where the interstellar wind is creating a bow shock in front of this thing that cannot be seen. We don't know much longer it will take to get outside our bubble, but every 3 years, Voyager 1 travels 1 billion miles. So we shouldn't have too many more years to wait before we pass the next major milestone in this humanity's farthest journey. So now I'd like to turn this to Suzanne, who will talk more about the spacecraft.
Thank you, Ed. I want to tell you that it's a pleasure to be here to talk to you about Voyager today. Voyager was my first job. It has a young engineer, a younger engineer, coming out of college. I started as an engineer before the Uranus encounter, and I've come a little bit full circle to come back as the project manager, and I'm just excited to be here. And I also think it's important to, as Ed has described to you, the history of Voyager, all the discoveries it's made in the past. But Voyager is still making discoveries, and it's important to get that message across to the public. This is not, we're not flying Voyager to fly an antique. We're flying Voyager to get new science information from it. And I want to talk to you today a little bit about this spacecraft and how it's an incredible workhorse, and how We continue to teach it new tricks and have it redo old tricks after a very long period of time. So as Ed has mentioned, if I can have the first slide. Oh, it's up, excuse me. As Ed has mentioned, where Voyager 1 is located currently is in an area of the heliosphere where we've now detected that there's no radial component to the solar wind. So it's almost in a dead zone. And we have asked the spacecraft to help us measure that area by doing a maneuver that it hadn't done since 1990, 21 years ago. We are using the low-energy charged particle, and I'm going to show you on the spacecraft where that is. The low-energy charged particle instrument is located here under the instrument boom, and it scans in a plane, in this direction, in this plane. And so what we did just this past March is we asked the spacecraft to maneuver, and so we rotated it along its long axis. We maneuvered it this direction, about 70 degrees, so it now scanned in a plane this way. And so that way we're getting, we're sensing in the environment in 3 dimensions. And so what we do with this maneuver is we rotate it 70 degrees, we hold it for 3 to 5 hours on gyros, and then we continue the rotation all the way around till it gets back to its original point and back to celestial lock. So if I can have the next slide. The last time we did this was back in 1990 when Voyager 1, just as it was leaving the solar system, actually Voyager 1 was out of the solar system, but it was done in 1990 where we could take an image of all the planets of our solar system has dots and put them all together in one image. And I think, as most people would agree, this is one of the iconic images from the Voyager spacecraft. It really puts your humanity in perspective of how small you are compared to how large our solar system is. Now, with this new roll maneuver that Voyager is doing, we plan to continue that every 3 months for the next 3 to 5 years until we hopefully reach the edge of the heliosphere and cross out into interstellar space. If I can have the next slide, please. This image shows you some of the spacecraft that have traveled out the most distance from Earth. In the upper left-hand corner, you can see Voyager 1. It's going up and out of the ecliptic plane. And in the lower left-hand corner, you see Voyager 2. It's going down and out of the ecliptic plane. Voyager 2 was actually launched ahead of Voyager 1 by 16 days. It's the older sibling by 16 days. But it's on a slightly slower, it's flying out at a slightly slower speed because it's on a different trajectory. But Voyager 2 has traveled for 12,273 days as of today. And Voyager 1 is the most distant spacecraft we have today. It passed Pioneer 10 in distance back in 1998. If you had an odometer on Voyager 1, it would be measuring currently 22.8 billion miles. Voyager 1 is 17.4 billion miles from the Earth. Voyager 2, again, is a little bit closer. It's 14.2 billion miles from the Earth. And Voyager 1 is, give you some speeds here, is 61,000 over 61,000 kilometers per hour is its speed, and for Voyager 2, it's just slightly over 55,000 kilometers is its speed. And the Voyager spacecraft continue, along with the Pioneer spacecraft, to travel out of our solar system. Next slide, please. So how do we talk to these spacecraft? I got to give a shout out to the Deep Space Network. They're the real workhorses for us. This is an image of the 70-meter antenna in Goldstone, California. These antennas were actually upgraded from 64 meters to 70 meters back in the late 80s for the Neptune encounter. And because our spacecraft are so far away, the signal is very, very faint. So we need the largest antennas in order to track the spacecraft. And I'm going to give you another kind of gee whiz number here. The time it takes for us to send a command from the Earth for it to reach Voyager 1 is slightly over 16 hours. And for Voyager 2, it's slightly over 13 hours. So for us to send a command, we go into the office Monday morning. We send a command to Voyager 1. And Voyager 1 says, yep, I got it. I'm going to send you a command back. We get that command back on Tuesday afternoon. 32 hours later. And to put that in perspective, a typical Mars mission has about a 10-minute one-way command time. So we're a lot farther out than Mars, a lot farther. If we enroll the last graphic I have, what's Voyager going to do in the future? Well, we have enough power on board to continue operating the Voyager spacecraft to 2020 and perhaps even out to 2025. The only fuel we use is really fuel for rotating the spacecraft. And we use a hydrazine fuel there. We use 1.6 grams a day. We have enough hydrazine fuel to last another 60 years. So that's not going to be any kind of a limiting resource for Voyager. But we're hoping to operate the spacecraft out to 2020 and maybe a little bit longer. We want to get across the heliopause, and we want to get out into interstellar space and take the first true measurements of interstellar space with an operating spacecraft. And when we reach that point, we'll be able to say that the Voyagers are truly traveling between stars. And now I'm going to hand it to Marat, and she's going to talk about her science.
Thank you. Before I describe some of the latest discoveries that Voyager gave us, I thought on telling a little bit of my personal journey into the Voyager team, and I hope I inspire another new, not so young like me, but younger people entering into the space science community and getting excited with the Voyager data and be engaged. So, and the next image show where I was around the time of Voyager was launched. I was back in Brazil, and this is an image. I am at the center. My twin sister, we're all wearing the same shirt on my side, and my dad is also an astronomer. We went to visit his radio telescope, this back in Brazil, so I was exposed to some science. And I remember in high school seeing some of the images of the Voyager was sending from the outer planets and being in awe. And fast forward a couple of years later, I accepted the position in the Jet Propulsion Lab to become a postdoc. And I remember coming into the von Karman auditorium and seeing the size of Voyager. It's fill out the whole auditorium. It's breathtaking. And you can imagine this huge apparatus. It's a huge machine flying into space. And I was thinking, oh my God, I'm going to go back to my office and analyze data. This incredible machine will be sending back. So this was incredible. And the other personal note here is, I was coming to space science from a different community, so I was not really familiar with space mission, with PIs. And I walk into the Voyager team meeting first time, and I see Ed Stone sitting at the head of the table, all these scientists sitting there, and I felt like I was coming to the Enterprise ship from Star Trek. I was like, where am I? And, it was scary. Like, the team is you can tell that they're analyzing the data and discussing the science for years. They're much older than me, and they're all guys. I was the only woman coming, so it was scary. And so it took me a while until I found my own voice, and I had courage to contribute to the discussion. But it was also amazing to hear them discussing. At that time, they were arguing if we cross the termination shock, and this is the boundary, as Ed was describing, where the solar wind become very slow, much slower than the sonic speed. And they was looking at data and trying to say, did we cross or not? So it was mind-boggling for me to realize how the science, you have to look very, very carefully at this data. It's a very precious data, and before, this is a legacy for the community of what we know about the solar system. So we have to be really, really careful of how to interpret this data. So this is a great experience. So let me tell you a little bit about the science. And as Ed mentioned early, I think Voyager wrote the books about what we know about outer planets. And I think we all agree that it's rewriting what we know about how stars interact with the interstellar medium, how it interacts with the medium that surrounds them, how the astral shifts look like. So it has lots of new discoveries. And one of the first discovery, let me show in the next image. This came from simulations like the one I'm used to do. So this is like a side view of our heliosphere, and this shows the magnitude of the interstellar magnetic field. This is the invisible force that engulfs us. The sun has its own magnetic field, but I'm showing here in red the intensity of the magnetic field outside our home. And maybe an analogy that gives you how much this is incredible, that we can sense what this magnetic field is doing. You know, sitting in your kitchen and you're measuring the weather outside your home. And this is what we're doing. We are with the Voyagers in the heliosheath, and we are able to sense enough from the data coming for Voyager to tell that our home is distorted, that the southern hemisphere is pushed in, and you can see Voyager 2 is in the south, is much closer to the sun than the northern hemisphere. So this was a major discovery. The next image show, if you would be in extraterrestrial heading towards our heliosphere, what you will see. So you will see our bubble, the heliosphere, but you will see distorted. It's not a smooth shape, and it's sidewise. So I like to think we're navigating through the interstellar medium sidewise. And this is, again, the effect of this force that I'm talking, the magnetic field outside our home, distorting us. And you can see Voyager 1 in red in the northern hemisphere, and Voyager 2 in the south. And it's nice to see that not just Voyager is seeing that. Other missions that are out there are seeing the same effect. So Voyager measure in situ. We're smelling, we're touching the ionized matter in the heliosheath. But there is other missions like IBEX and Cassini, please bring the next image, that give us a map of what is out there. So this is an image, not like the previous one, that is an image from outside looking back to our heliosphere. This is an image from inside, from Earth looking out, or from Cassini, from Saturn looking out, and mapping these energetic neutrals that come to us. And without going all the details in that, you can see that these bright features in IBEX in the upper part, and in Cassini in the lower, the red feature, see that these emissions, these neutrals, are not uniformly spread out. There is something organized in the data. And again, we think this is the interstellar magnetic field. So this is all coming together, these all missions. And what is exciting, what we're heading for the future, is not only we are for the first time in this brand new media, the heliosheath, and we are discovering that it's very different than what we thought. The magnetic fields behave different, the ionized matter behave different, so we're still trying to uncover this, and we are heading towards, as Ed was mentioning, the heliopause. We never cross the boundary like that, so we don't really know what to expect. So we're all holding our seats that we will be able to say, yes, we crossed, and not still pondering, looking at the data, did we cross, we didn't cross. So this is a very exciting period for Voyager. And you can see in the next image, the WISE image of a bow shock. It's a beautiful image from the dust around that map, the bow shock. But this is a remote image. And Voyager will bring us for the first time in situ measurement, the smell, the touch of what is an astrosheath. So I will pass now to Anne, that will give you what the message that Voyager had to give us.
Thank you, Marat. So the Voyager mission is that intersection of exploration, our first epical reconnaissance of the outer solar system, our first close-up look at 60 new worlds. It's also scientific research in that it's telling us the actual shape of the solar system as we move through the galaxy, and much more than that. But it's also a cultural and emotional and even a spiritual artifact for the human species. We are looking at the Golden Voyager record, which contains some 27 pieces of music. It's considered, in fact, the origin of that concept of world music. 116 pictures of what life on Earth is like, from our most beautiful buildings to human beings and the other creatures with which we share this planet. Greetings in some 50 languages, including the beautiful songs of the humpback whales, and 5 languages that are no longer spoken, ancient languages with no speakers, as well as the most populous languages spoken on Earth today. And there's a sound essay on it, which includes a mother's first words to her newborn baby, and a baby's first cry, the brainwaves of a woman newly fallen in love, the sound of the geological history of the Earth, its biological evolution, and our technology, and what was then our recording of the most distant object, which was a pulsar. And all of this is, may I have the next slide, please, is encased in a golden cover, engraved with scientific hieroglyphics, instructions for play to the putative extraterrestrials we imagine might intercept it one day. And as you can see, that circle is the record itself, with the stylus that we included for play. You know, this is the 1970s when people were listening to records, and I'm really excited about the fact that musicians and lovers of music are returning to records as being richer in sound and information than digital recording. And there's also an atomic clock which will date when the record was launched and when the message was sent, and then our address in the galaxy, the 16 closest pulsars, just to give a little sense of where this came from. Now, I'd like you to listen to some of the sounds and some of the music included on Voyager. These are only tiny snippets of a much longer Voyager message, as well as to see just a handful of the images that are included on Voyager. And I ask you to imagine yourself an extraterrestrial who knows nothing of our planet and who's getting a first glimpse of what life on Earth is like and what it sounds like. Thank you. Let's please play it.
Hello from the children of planet Earth.
That gives you just some idea of the Voyager record. You know, it was originally the idea of Carl Sagan and Frank Drake to send this message because of this gravitational assist from the massive planet Jupiter. The 2 Voyager spacecraft were flung out of the solar system and are expected to wander at speeds of something like 40,000 miles an hour through interstellar space for 1,000 million years. And the geniuses who designed the mission trajectories so that these two spacecraft could rendezvous with these planets and moons and flawlessly send back to us these images of the outer solar system. And the idea that this spacecraft is still functioning, that a young person in the audience today, a child in this audience, it's possible they could come to maturity and become a scientist or a technician or a mathematician or an engineer. And the Voyagers will still be thriving. This is the result of the genius of NASA. And I'd like to show a few pictures of the men and women who were involved in the Voyager mission. In those days, it was largely men, and I'm happy to point to the shift in the ratio here on the panel today. But these guys, you know, they did something that is absolutely the equal of Magellan or Columbus or any of the great explorers of terrestrial discovery. And yet, how many of us know the name Charlie Colhayes or Gary Flandreau or Michael Minovich? These guys should be on the stamps because, you know, if we don't value the genius behind building a machine with 1970s technology, you know, virtually out of transistors, to that one that functions so brilliantly today, and to be able to do this exploring for us. If we don't value their contribution, then is it any wonder that so few of our children are really interested in doing what they did? So I just wanted to say what an amazing contribution to our civilization, and the fact that perhaps 100 million years ago or 500 million years ago, Voyager's greatest triumph is yet to come. It will sing for us and speak for us long after the very continents of our planet have changed. That's an epical achievement. And I think when people ask, you know, why spend money on space exploration when we have so many problems here? Well, that's a perfectly good question. But I think we have to do both things. And I think that the Voyager has exceeded its design specifications and the loftiest dreams of its makers. And I'd like to go back to the family portrait of our solar system and to talk about the maturity of our species, that we are now in a position to look at the other worlds of our solar system only 400 years after Galileo's first look through a telescope. This is the awesome power of the scientific method. And looking at that family portrait, I'm reminded of the fact that Carl Sagan, who was a member of the Voyager imaging team and very much involved in the project, he asked that Voyager's cameras be turned to look homeward one last time before they were turned off, to take one last picture. And he was largely responsible for urging NASA to take this image of our world, not the Apollo frame-filling world, which in itself was a major paradigm shift for our culture and our civilization globally. But now to see us in something that reflects more clearly our true circumstances in the cosmos, that pale blue dot in that circle. And I'd like to close this phase of our talk with the words of Carl Sagan in his meditation on that image and what it could mean for all of us. Thank you.
Consider again that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The Earth is a very small stage in a vast cosmic arena. Think of the rivers of blood spilled by all those generals and emperors, so that in glory and triumph they could become the momentary masters of a fraction of a dot. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known.
Something to think about, ladies and gentlemen. Words profound then, as they are still now. Before we open it up for questions, I would like to inform folks that deep space missions like this are enabled by a very unique power source called a radioisotope thermoelectric generator. It, in essence, is essentially a nuclear battery that enables incredible missions like this. And for more information on this incredible power source, very safe and clearly very reliable as a result of the amazing story here and other missions for 50 years, go to www.nasa.gov and learn more about this incredible power source. And this power source also will be going to Mars in another version, advanced version, Mars Science Laboratory or Curiosity, another amazing mission. Now, we're going to do something different here. We have a national audience viewing this program, and in that national audience are numerous students in schools. And this is what we are about, ladies and gentlemen. This is what these amazing people are about. So we're going to take questions from these schools, which we have. We received many, many. And for the schools listening, you can still send in your questions. The wonderful folks at the Jet Propulsion Lab and the Education Outreach Department will answer your questions. So post answers on the web at www.nasa.gov/Voyager. But we're going to take a trip around the nation here with the schools who are here because this is what it's about, inspiration. We're going to go to Columbia, South Carolina. And this is a question for you, Suzanne, from Miss Carboni's 7th and 8th grade math classes, Creighton Middle School. What have we learned from Voyager's technology that is being applied to current and future NASA space exploration missions?
Oh, okay, thank you, Dwayne. So there, I think, are many technology firsts that Voyager pioneered that were used by follow-on missions such as the Galileo mission to Jupiter and the Cassini mission to Saturn. I'm going to highlight just a couple of them for you here. When the Pioneer spacecraft went by Jupiter ahead of Voyager, they discovered a very strong radiation field, and that got the engineers at JPL thinking, we've got to do something different for Voyager or we won't survive the flyby of Jupiter. So the engineers at JPL came up with the technique of using radiation-hardened electronic parts. And what you're doing here is that you're shielding and screening the electronics so those high-energy charged particles can't damage them. So that was one technique that's been used on practically every spacecraft since then. Certainly every spacecraft that's going to a Jupiter or a mission with someplace where there's a high radiation field. And I think another great first for Voyager was the use of a programmable command processor. The Voyager mission today wouldn't be what it was without the ability to change the commanding of Voyager as it got further out to longer distance planets and then into the Voyager interstellar mission. And you will not see a spacecraft today that doesn't fly without a commandable processor, and that was developed first for Voyager. And a little anecdote that's similarly related to that, Voyager is flying with only 68 kilobytes of memory between three computers. Now, when you guys walk home and take the subway home, or you school kids are you put on your earphones and you turn up your iPad, or excuse me, your iPod Nano. I want you to think about that. Has 8 gigabytes, or 8 gigabytes of memory. So it's got 100,000 times more memory in your iPod than it does in the Voyager spacecraft. So I like to use that anecdote a lot to relate to how technology changes rapidly.
Thank you, Suzanne. Marav, you're up next from Mrs. Laura Jeck. 7th graders, homeschool program in the Morgan Hill Unified District in San Jose, California. Please discuss 1, 2, 3 of the most important changes about our understanding of the heliosphere and interactions with fluff that must be changed or updated as a result of Voyager's discoveries.
Thank you, Dwayne. Well, some I already kind of discussed when I was talking about the science discoveries. One major one was the fact that our heliosphere is asymmetric, that it's pushed in the south rather than in bulging out in the north. This is one major discovery. The other one is that the magnetic field, this invisible force that lies in the interstellar medium, the medium ahead of us, has an orientation that, this is what our measurements are telling us, that is not in the same direction as the Milky Way, the disk of our galaxy. That this is the field in really large scales. So something happened between the really big scales where the stars are until getting closer home. The weather changed. We don't know why, we have some ideas, but there is a different orientation, and it has a strength that is pretty strong. So it has some implications that it might be a dominant energy outside our home. We don't know. There's another discovery, harder to explain, but one of the interesting things that when Voyager 2 crossed the termination shock, the region where the solar wind is very slow, the temperature of the helios sheets was much lower, was an order of magnitude lower than what we expected. And Voyager measured the thermal ionized matter. So this energy went somewhere else. And we think it went to what we call superthermal particles, very energetic particles. So it just makes us think how fluids, how ionized goes through shocks. We have to rethink about it, where the energy goes. So this was
Thank you. Okay, now we're going to Kettering, Ohio, Van Buren Middle School. And this is for you, Suzanne. Mr. Doe and Mr. Lowles, 8th grade cyber science and science classes. We read an article on the Voyager website that says Voyager 1's plasma instrument was broken, but the one on Voyager 2 was working fine. How did NASA know that the plasma instrument on Voyager 2 was working properly? Suzanne?
Thanks, Wayne. Well, the plasma instrument measures the lowest energy charged particles in the solar wind, and it measures both the speed and the direction of those particles. Now, when Voyager 1 went past Saturn, there was a failure with the high voltage modulator on the plasma instrument, and it basically rendered the instrument incapable of getting any significant data back. Now, Voyager 2, the plasma instrument is still operating. We're still taking data with it. When we get that data back, we analyze it and we compare it to our models, and we compare it to data from other spacecraft. And because those tend to match up, we believe that the data we're getting back from the plasma instrument is accurate, and that the instrument is functioning properly on Voyager 2.
Thank you. And a question for you. And this comes from Union, New Jersey. Mr. Petrus, 6th, 8th grade gifted and talented students from the Union Middle School. What made astronomers decide to record the things they did on the golden disk? What makes astronomers think that their directions were straightforward enough for these creatures to listen to the disk or understand the images?
These are really two great questions. Let me take the one about the instructions for play and our cosmic address. Even though Voyager has a very long future, as described earlier, perhaps 1,000 million years, wherever it goes in that area, the laws of physics will be the same. And that's the only common language that we can hope to have with these imagined extraterrestrials. Remember, we have yet to receive any evidence that they exist, but we look at the enormity, the vastness of the universe and the number of worlds and the processes that led to the origin of life on Earth, and we suspect they may be out there, but that's different from knowing. But if they are out there, the only way that the Voyager record is going to be intercepted, because space is so mostly empty, the emptiness of space cannot be exaggerated. So we're not imagining that one of these spacecraft will collide with a world and someone will, on that world, will find the record. We're imagining that spacefaring extraterrestrials will flag it down. Now, if you're smart enough to travel in space, then we'd like to bet that you're smart enough to figure out what we're trying to say in the hieroglyphics. So that was the reasoning behind it. And the second part of the question is, well, how did we choose this? And it wasn't just astronomers. It was artists, writers, musicians, ethnomusicologists, people who study the history of music. There were many, many people involved. And we decided to go for a complete picture of our planet. And so we wanted to represent all of the world's great musical traditions. We didn't want it just to be from our American point of view. We wanted to show really a planetary perspective, and that's what science and astronomy and missions like Voyager do. They make you think in terms of your planet. And so every piece could be considered a kind of a tile in a much greater mosaic. So we have a 12-year-old child singing, and we have a 95-year-old virtuoso on the Chinese qin, a stringed instrument, playing one of the pieces. We have images of day and night, young and old. Everything was chosen so not just for its intrinsic value, but for its ability to fill in another blank in the puzzle of what life on Earth is like.
Thank you. We're going to use the remaining time for just two more questions, and I want to remind all of the students out there in the nation and across the world that you can still send in your questions at nasa.gov/Voyager, and your questions will be posted, and we'll get you answers as quickly as possible. So keep those questions coming in. Ed, we're coming back to you. This is from Northwest Arkansas Community College. Dixie Andros, College Course, Survey of the Universe. Do we anticipate seeing higher concentrations of charged particles from interstellar space in the outer region of the heliopause perimeter? If yes, why? If no, why not?
Well, that's a wonderful question. It turns out that inside the solar bubble, the magnetic field comes from our sun, just like the solar wind comes from our sun. The solar wind carries it out. Outside, the wind comes from these other stars that blew up, and the magnetic field comes from those other stars. And in fact, because the magnetic field is different inside and outside, the ions outside cannot easily get inside, and those inside can't easily get outside. That's the reason all the solar wind goes down the tail. Now, at the boundary itself, there is probably some turbulence, and we are starting to talk about what we expect to see, because it's unlikely that we understand exactly how this interface is between these different winds. And I suspect, like in the past, we will be surprised, and we may in fact have a debate for a year or two before we finally decide we have crossed the boundary.
Okay, our last question, and this is definitely from Marav because we're going to go to Brazil. Denise Selmo, high school English teacher, Santa Maria in Sao Paulo.
Sao
Did I
Paulo.
get that right?
Yeah.
Is it possible that some of the particles detected by Voyager can carry information about some kind of life out of our solar system?
It's a very good question. Hola. What Voyager detects is not molecules, so it cannot really detect directly any signatures of life out there. But it detects atoms, and atoms are the building blocks of life. So we are inferring what you call abundances. So you're inferring how much atoms of each type are out there. Once we cross to the interstellar medium, we will learn also what lies outside the solar system. And this is the building blocks of life. So indirectly, we will learn.
Great. Well, we're gonna wrap it up here. What I would like to do, I would be remiss that when we do incredible and amazing missions like this, we don't do it alone. And I talked about the power source, the RTG, and the version that will be on Mars Science Lab. These are built by the Department of Energy, so it is an incredible relationship we have when we do deep space missions. It's a partnership, and it works very well. I want to thank these amazing folks. May we please give them a round of applause for the story. Amazing story by amazing people, and you guys are amazing, NASA and everyone. Thank you for joining us. Have a wonderful day.